Alright, so yesterday we were talking about um, the addition rule, and we talked about mutually exclusive. So remember, mutually exclusive means what? They cannot both happen. So the probability that both things occur is 0. It's impossible for both of them to occur at the same time. Alright, today we are going to be looking at independence, and we're going to talk about the multiplication rule. So yesterday we were asking or. What's the probability of this or this? And or meant that we had to add the probabilities. Today we are going to be talking about and statements. And for and, we will multiply the probabilities. So, or means add, and means multiply. That's something that we will have to remember moving forward. You'll also see it on your formula sheet because you don't have to memorize any of these formulas. They are all there for us. So starting off, we need to know independent versus dependent events. So independent is the occurrence of one does not affect the probability of the other. Okay, so an independent event might be you drinking your milk at lunch today and me teaching probability when you come to this classroom. Do they have anything to do with each other at all? No. Knowing that you drank milk does not change the probability of me teaching stats or vice versa. Dependent is when the occurrence of one changes the probability of the other. So if I said the probability that it rains today and the probability of having a softball game, would those be independent or dependent events? Dependent, because if it rains, what happens to the probability of having a softball game? It's going to go down. Knowing one thing happened will change the probability of the other. So that's independent and dependent. Let's practice that. So looking at these examples, decide if they are independent or dependent. Suppose you draw a card from a standard 52 card deck of cards and then roll a die. So the events draw a heart and roll an even number.
Or
Independent. The number I roll does not change because of the card I took out of the deck. B. Suppose two 40-year-old women who live in the United States are randomly selected. The events woman 1 survives a year and woman 2 survives a year. So I'm taking 2 women in the entire United States. So I might have one 40-year-old woman in New York and then a 40-year-old woman in Utah. If one of those women lives the entire year, does that change the probability of the other one? No, they're completely unrelated. Okay, suppose 2 40-year-old women live in the same apartment complex. The events woman 1 survives a year and woman 2 survives a year. Would those be independent or dependent? So, okay, so is there the potential, if I know that that apartment catches on fire, would their probabilities of surviving be somehow intertwined? Yes. Now, does that mean that if one of them dies, the other one will? Absolutely not. But because they are living in such close proximity, there could be factors that would affect both of their probabilities. If there was an earthquake or some kind of natural disaster right there, that would impact both of them because of their close proximity to one another. So these would be dependent. Okay, it doesn't mean that there is necessarily a large chance that both would be impacted, but there is events are totally independent, then to find the probability that both occur, all we have to do is multiply the individual probabilities. So on your formula sheet, it has the back of that first page, multiplication rule for independent events, in this exact formula. So I could do the probability that you drink your milk times the probability that I teach statistics and get the probability of both things occurring. It doesn't have to be limited to 2 events. So it might be you drink your milk, I teach statistics, and Megan has her phone in her pocket.
I'm done.
So I could have 3 or 4, or I could add in, the probability it rains outside. So if I want the probability of all of these things happening, all we're just doing is multiplying the individual probabilities. Alright, so the probability that a randomly selected 60-year-old female will survive the year is 99.186%. What is the probability that 2 randomly selected 60-year-old females will survive? So what do I have to do?
Multiply 99.18 or 0.59186.
The probability they both survive is the probability the first survives times the probability the second survives. Okay, they have the same chance. So I get 0.983. Okay. What is the probability that 4 will survive the year? So what would I do? Yep, we have to do this 4 times. Or I could just say to the 4th power. We get 0.967. Is that one okay? So same scenario, we have still the randomly selected 60-year-old female, same probability they survive. What is the probability that at least 1 of 500 randomly selected 60-year-old females will die during the course of the year? Okay, so the probability that at least 1 of them dies. So that could mean exactly 1, or 2, or 3, or 4, all the way up to 500, right? So how could I calculate that without having to do all these different possibilities?
1 minus 99 or 0.99186.
Very close. The probability that at least 1 dies. Isn't that the opposite of everybody surviving? So we could just do 1 minus the probability they all survive. And it's pretty easy to find the probability they all survive. If I have 500 people, what would I have to do? So we're just really using the complement here. So there is over a 98% chance that somebody will not survive the year. Is that okay? exercise equipment knows that 10% of their products are defective. They also know that 30% of their customers will actually use the equipment in the first year after it is purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So they're basically trying to figure out how many of these are we actually going to have to replace. We know 10% of our products are bad, but if somebody never uses it, will they figure out there's something wrong with it? No, and if only 30% of the people are actually using it, there's a pretty good chance that they're never going to use it, so they'll never have to replace it if something's wrong with it. Okay, so the only way there would be a valid warranty claim is if the product is bad and the person uses it to find out. So we basically need to find the probability that it is defective and no problem.
Okay. And then I will also take
And you, okay, and the ruler and calculator as well. Thank you. So, we have to find the probability that the equipment is defective and they use it. Are these being defective and being used, is that independent or dependent? Independent, because does the customer even know if it's defective when they first open it? So it's not like they're going to know it's defective and therefore not use it. Okay, those are two independent things. So all we have to do is probability that it's defective times the probability they actually use it. So probability being defective is 0.1, the probability that they actually use it. And if we multiply, we get,
0.03.
so there is only a 3% chance that they will have to replace the equipment. Any questions on that? So this is a very short section. We're pretty much done. We have not talked at all about how to find the probability when they are dependent. That's going to be our focus tomorrow because there's a little more to that. But just kind of a recap of where we're at so far. We know that any probability always has to fall between 0 and 1. And when I add up all my probabilities, we have to get 1 every time. We know that if they are disjoint, so that means mutually exclusive, so no overlap, then to find the probability of one or the other, we just add them. If they're not disjoint, we have to subtract off the overlap, subtract off the E and F. We know that the complement is the opposite of our event, so that's 1 minus our probability. And we have that if they are independent, the probability of both things occurring, we just multiply. Okay, so that's where we're at so far. We really only have one more section in this chapter. It's kind of flying by. But we're going to cover that section tomorrow. And then we'll take a couple days just kind of putting all of it together. So I have basically one more day of teaching you new probability stuff, and then we're going to do several days of practicing all of it from there. So I'm going to give you time to work on homework. Same standing rule, if any of the problems say find and interpret the probability, you don't have to interpret.